Introduction to Apache Mahout. 1. Machine Learning Library. Apache Mahout is an open-source machine learning library designed for creating scalable and performant machine learning applications. 2. Scalable Algorithms. Offers a wide range of pre-built algorithms for clustering, classification, and collaborative filtering that are scalable. 3. Integration with Hadoop. Mahout integrates seamlessly with Apache Hadoop for handling large datasets. 4. Diverse applications, suitable for a variety of applications, including recommendation systems, fraud detection, and text mining. Architecture of Apache Mahout. 1. Modular structure. Mahout has a modular architecture, making it extensible and adaptable for different machine learning requirements. 2. Algorithm libraries. Contains a rich set of algorithms optimized for distributed computing environments. 3. MapReduce and Spark. Supports both MapReduce and Apache Spark for parallel processing of large data sets. 4. Data model adaptability. Designed to adapt to various data models, making it suitable for a wide range of datasets and applications. Challenges in Apache Mahout. 1. Complexity in implementation. Implementing Mahout algorithms can be complex, requiring a good understanding of machine learning concepts. 2. Scalability concerns. Ensuring scalability while maintaining performance is challenging, especially with very large datasets. 3. Algorithm limitations. Some algorithms may not be optimized for all types of data, leading to limitations in certain applications. 4. Integration challenges. Integrating Mahout with other systems and platforms can be complex, requiring careful planning and execution. Best practices in Apache Mahout. 1. Data preparation. Properly prepare and clean data to improve the accuracy and efficiency of machine learning models. 2. Algorithm selection. Choose the most suitable algorithms for specific problems and datasets to achieve optimal results. 3. Resource management. Efficiently manage computational resources when processing large datasets to ensure performance. 4. Continuous learning. Continuously refine and update models with new data to maintain accuracy and relevance. Introduction to Apache Ignite. 1. In-memory computing platform. Apache Ignite is an open-source in-memory computing platform, enhancing speed and scalability of applications. 2. High performance and scalability. Provides high-performance computing capabilities, handling large-scale data processing. 3. Data Grid and SQL Query Engine. Features a distributed data grid and SQL query engine for real-time data processing and analytics. 4. Versatile integration. Easily integrates with Hadoop, Spark, and other big data frameworks. Architecture of Apache Ignite. 1. Distributed cluster architecture, built on a peer-to-peer architecture, enabling distributed computing and storage. 2. In-memory data grid, provides a robust in-memory data grid for rapid data access and processing. 3. Compute Grid and Services, offers compute grid functionalities for executing complex logic and services. 4. SQL and streaming capabilities, supports SQL queries and real-time data streaming for analytics. Challenges in Apache Ignite. 1. Memory management. Efficiently managing in-memory resources is crucial for optimal performance. 2. Cluster management. Ensuring stable and efficient operation of distributed clusters can be complex. 3. Data consistency. Maintaining data consistency across distributed nodes is a significant challenge. 4. Scalability and performance. Balancing scalability with performance requires careful tuning and configuration. Best practices in Apache Ignite. 1. Data partitioning. Effectively partition data across the cluster to optimize performance and resource utilization. 2. Backup strategies. Implement robust backup strategies for data resilience and recovery. 3. Performance tuning. Continuously tune performance parameters to handle workload variations. 4. Regular monitoring. Monitor cluster health and performance regularly to identify and resolve issues promptly. Introduction to Apache Impala. 1. Open source SQL query engine. Apache Impala is an open source, distributed SQL query engine for big data. 2. Real-time query performance, provides high-speed, low-latency SQL queries on Hadoop. 3. Hadoop ecosystem integration, seamlessly integrates with the Hadoop ecosystem, supporting HDFS, Apache Base, and Apache Hive. 4. Massively parallel processing, utilizes MPP, massively parallel processing, for fast analytics on large-scale data. Architecture of Apache Impala. 1. Distributed architecture, Designed with a distributed architecture, enhancing scalability and performance. 2. Daemon process on each node. An Impala daemon runs on each node in the Hadoop cluster, processing queries. 3. SQL query execution. Efficiently executes SQL queries using distributed query execution. 4. Use of HDFS and HBase. Leverages HDFS for storage and integrates with HBase for real-time queries. Challenges in Apache Impala. 1. Resource management. Effectively managing resources across a distributed environment. 2. Query optimization. Optimizing queries for varied workloads and data distributions. 3. Scalability. Scaling to accommodate growing data sizes and query complexities. 4. Fault tolerance. Ensuring robust fault tolerance in case of node failures. Best practices in Apache Impala. 1. Efficient data storage. Use efficient data formats like Parquet for optimal performance. 2. Query performance tuning. Continuously tune and optimize queries for faster execution. 3. Cluster configuration. Properly configure the cluster for balanced workload distribution. 4. Monitoring and maintenance. Regularly monitor system performance and maintain the cluster for stability. Introduction to Apache Kudu. 1. Open source storage engine. Apache Kudu is an open source storage engine designed for the Hadoop ecosystem. 2. Fast analytics on fast data. Optimized for fast analytics on rapidly changing data. 3. Integration with Hadoop ecosystem. Seamlessly integrates with Hadoop's analytical tools like Apache Spark and Apache Impala. 4. Columnar storage format. Utilizes a columnar storage format to enable efficient analytics and high-performance scans. Architecture of Apache Kudu. 1. Master tablet server architecture. Employs a master server architecture for managing tablet servers, which store data. 2. Data partitioning. Data is partitioned across tablet servers for scalability and performance. 3. Write and read paths. Optimized write and read paths for low latency operations. 4. Consistency model. Provides strong consistency through Raft consensus protocol. Challenges in Apache Kudu. 1. Resource management. Efficient management of memory and disk resources across tablet servers. 2. Data balancing. Ensuring even data distribution and balancing across servers. 3. High availability. Maintaining high availability and minimizing downtime. 4. Backup and recovery. Implementing robust backup and recovery mechanisms for data integrity. Best practices in Apache Kudu. 1. Schema design. Designing efficient schemas that leverage Kudu's columnar storage for optimal query performance. 2. Cluster sizing. Properly sizing the Kudu cluster based on workload requirements. 3. Performance tuning. Regularly tuning performance settings for optimal operation. 4. Security implementation. Implementing security measures like Kerberos for secure data access. Introduction to Amundsen. 1. Metadata search and discovery tool. Amundsen is designed for efficient metadata search and discovery within an organization. 2. Open source project. Developed as an open source tool to aid data-driven companies in managing their data assets. 3. Integration with data sources. Capable of integrating with various data sources like databases, data lakes, and warehouses. 4. Use in data governance. Plays a significant role in data governance, enabling better understanding and usage of data. Architecture of Amundsen. 1. 3-tier architecture. Comprises of a metadata service, search service, and front-end service. 2. Metadata extraction. Ingests and stores metadata from various sources for easy access and management. 3. Search and exploration. Provides a powerful search interface for users to explore and find relevant data. 4. Front-end service. User-friendly front-end for navigating and interacting with metadata. Challenges in Amundsen. 1. Scalability. Managing scalability as the volume of metadata grows. 2. Metadata quality. Ensuring the accuracy and relevance of metadata. 3. Integration complexity. Integrating with a wide range of data sources and types. 4. User adoption. Encouraging users to consistently utilize the tool for data discovery. Best practices in Amundsen. 1. Regular metadata updates. Keep metadata up to date for accurate search and discovery. 2. User training and engagement. Train users for effective utilization and engagement with the tool. 3. Data source management. Efficient management of integrations with various data sources. 4. Monitoring and maintenance. Regularly monitor and maintain the system for optimal performance and usability. Introduction to Apache Atlas. 1. Data Governance Framework. Apache Atlas is designed as a comprehensive framework for data governance and metadata management. 2. Open Source Project. It is an open source tool, facilitating widespread usage and community-driven enhancements. 3. Metadata Management. Centralizes the management of enterprise metadata, offering rich classification, cataloging, and lineage capabilities. 4. Compliance and Security. Enhances data security and compliance through effective governance. Architecture of Apache Atlas. 1. Pluggable architecture. Designed with a pluggable architecture for easy integration with various data sources. 2. Metadata Store. Utilizes a scalable and robust metadata store for efficient management and retrieval. 3. Extensible Model. Offers an extensible model for custom metadata types and entities. 4. Integration Hooks. Provides hooks for seamless integration with other Hadoop components and third-party applications. Challenges in Apache Atlas. 1. Complex setup. Initial setup and configuration can be complex and time-consuming. 2. Scalability. Managing scalability with increasing data and metadata volumes. 3. Metadata quality. Ensuring high quality and consistency of metadata. 4. Performance optimization. Continuously optimizing performance for large-scale environments. Best practices in Apache Atlas. 1. Consistent metadata standards. Apply consistent standards and practices for metadata management. 2. Regular monitoring. Regularly monitor the system for any issues or performance bottlenecks. 3. Effective integration. Ensure effective integration with other data governance and management tools. 4. Community engagement. Leverage the Apache Atlas community for support, updates, and best practices. Introduction to Apache Pulsar. 1. Distributed Messaging System. Apache Pulsar is an open-source, distributed messaging and streaming platform. 2. High Throughput. Designed for high throughput and scalable performance. 3. Low Latency. Offers low latency delivery of messages for real-time processing. 4. Multi-tenancy. Supports multi-tenancy with strong isolation and security features. Architecture of Apache Pulsar. 1. Decoupled architecture. Features a decoupled architecture for messaging and storage. 2. Geo-replication. Supports geo-replication across multiple data centers. 3. Persistent storage. Utilizes Apache Bookkeeper for durable and persistent storage. 4. Broker and Bookkeeper. Separates the roles of brokers, serving clients, and bookkeepers, managing storage. Challenges in Apache Pulsar. 1. Operational complexity. Managing and operating a Pulsar cluster can be complex. 2. Resource management. Efficient management of resources and capacity planning. 3. Data consistency. Ensuring data consistency and reliability across distributed environments. 4. Scaling. Scaling the system in response to workload changes can be challenging. Best practices in Apache Pulsar. 1. Effective monitoring. Implement comprehensive monitoring for performance and fault detection. 2. Load balancing. Ensure effective load balancing for optimal performance. 3. Disaster recovery. Plan and implement disaster recovery strategies for data safety. 4. Security measures. Implement robust security measures including authentication and authorization. Introduction to Apache *DB. 1. Big Data Management System. Apache *DB is an open-source, distributed big data management system. 2. Scalability. Designed to efficiently store, manage, and query large volumes of data. 3. Flexible Data Model. Supports a semi-structured, NoSQL-style data model. 4. Query Capability. Provides rich querying and indexing capabilities. Architecture of Apache *DB. 1. Distributed storage. Built on a distributed architecture, handling large-scale data across nodes. 2. Partitioned indexing. Uses partition B tree and R tree indexes for efficient data retrieval. 3. Query optimization. Employs advanced query optimization techniques for complex data. 4. Data model flexibility. Offers a flexible data model, accommodating varied data types. Challenges in Apache *DB. 1. Data skew. Managing data skew in distributed environments. 2. Large-scale deployment. Challenges in deploying and managing at a large scale. 3. Query performance, optimizing query performance over varied and large datasets. 4. Data consistency, ensuring consistency and integrity of data in distributed setups. Best practices in Apache *DB. 1. Efficient data modeling, adopt a data model that efficiently represents and accesses data. 2. Indexing strategies, use appropriate indexing strategies for better query performance. 3. Monitoring and tuning, regularly monitor and tune the system for optimal performance. 4. Data security, implement security measures for data protection and access control. Introduction to Apache Tinkerpop. 1. Graph Computing Framework. Apache Tinkerpop is an open-source, graph computing framework. 2. Language agnostic, provides compatibility with numerous programming languages. 3. Extensive libraries, offers a wide range of graph-related functionalities through its libraries. 4. Industry adoption, widely used in various industries for complex graph data processing. Architecture of Apache Tinkerpop. 1. Gremlin Query Language, features Gremlin, a powerful graph traversal language. 2. Pluggable backends, supports various graph database backends. 3. Standard APIs, offers standardized APIs for graph operations. 4. Modular components, comprises modular components for flexible graph computing. Challenges in Apache Tinkerpop. 1. Query complexity, handling complex queries in Gremlin can be challenging. 2. Performance scaling, ensuring performance at scale with large and complex graph data. 3. Learning curve, steep learning curve for new users, especially with Gremlin syntax. 4. Integration complexity, integrating with various backend systems can be complex. Best practices in Apache Tinkerpop. 1. Efficient query design, design efficient Gremlin queries to optimize performance. 2. Choosing the right backend, select the appropriate graph database backend based on needs. 3. Regular optimization, continuously optimize graph models and queries. 4. Proper indexing, implement appropriate indexing strategies for faster query processing. Introduction to Apache Carbon Data. 1. Hadoop-based file format. Apache Carbon Data is an indexed columnar data format optimized for fast analytics on big data platforms like Apache Hadoop. 2. High performance, delivers high-speed data processing and analytics. 3. Efficient data storage, utilizes advanced compression techniques for efficient storage. 4. Data scalability, effectively handles large volumes of data, ensuring scalability. Architecture of Apache Carbon Data. 1. Columnar storage, stores data in a columnar format, enhancing read performance. 2. Indexing mechanism, implements indexing to speed up data retrieval. 3. Hadoop integration, seamlessly integrates with Hadoop ecosystems. 4. Query optimization, optimizes queries for faster execution on big data. Challenges in Apache Carbon Data. 1. Data management complexity, managing data effectively across distributed environments can be complex. 2. Performance tuning, requires fine-tuning for optimal performance in varied scenarios. 3. Integration with ecosystem, integrating with different components of the Hadoop ecosystem can be challenging. 4. Handling evolving data, adapting to changing data patterns and volumes. Best practices in Apache Carbon Data. 1. Efficient schema design, create an efficient schema for better data organization and retrieval. 2. Optimal indexing strategy, employ an effective indexing strategy for faster query processing. 3. Regular performance checks, conduct regular performance assessments and tuning. 4. Effective data partitioning, implement data partitioning to improve query performance and manageability. Thanks for watching.